Hi everyone, I'm Krishna and I'm excited to present our project on deep learning for skin cancer detection, developed as part of Team 45 alongside Soumya and Gnome. Our work focuses on HAM 10,000 dataset and CNNs to classify skin lesions and assist in early detection of skin cancer. The motivation of the project is that skin cancer is among the most common forms of cancer globally, and early detection can significantly improve outcomes. Dermatologists achieve great accuracy in classification, but access to such expertise isn't always available, especially to poor and remote areas. So our goal was to build a deep learning model that can match expert level performance and potentially be deployed to mobile apps for broader accessibility. So our problem statement is that the core problem we are tackling here is to build a CNN model to classify 7 types of skin lesion. And along the way, we face several challenges like handling class imbalance, improving sensitivity, etc. And we evaluated performance using metrics such as accuracy, sensitivity, and AUC, obviously. And as for the dataset source, we use the HAM 10,000 dataset from Kaggle. It includes over 10,000 images across 7 labeled classes, including both benign and malignant lesions. Each image is high resolution at around 600 cross 450 pixels, and the dataset also contains metadata like diagnosis and lesion location. And as for the inputs and outputs, our model takes in RGB images along with optional metadata and outputs the predicted class of the lesion along with confidence score for each class.
So we started with a simple baseline CNN and then applied a series of optimization. These included data augmentation like flipping and zooming to improve generalization, batch normalization to stabilize learning, dropout layers for regularization, and increasing the number of convolutional layers to capture more complex features. We also used early stopping and a more robust training pipeline with real-time data generation. So let's take a closer look at the training curves for both our baseline and optimized models. So for the baseline model, training accuracy kept climbing steadily and reached over 80%. At first glance, that sounds great, but if we look at the validation accuracy, which is performed on unseen data, it peaked early around 75%, then started to drop and fluctuate. So this mismatch between training and validation accuracy indicates overfitting. So basically the model was memorizing the training data rather than learning meaningful patterns that generalize to new images. So in contrast, the optimized model showed a much healthier learning behavior. Both training and validation accuracies increased together and stayed closely aligned, eventually stabilizing around 70%. So the small gap between the two curves is a strong sign of good generalization. It means the model is learning robust features, not just memorizing. So even though the training accuracy is slightly lower than the baseline, this trade-off leads to a model that's more reliable in a real-world usage. So now on to the confusion matrix. This gives us a more granular look at how the model performs across different classes. So in the baseline model, we saw that most predictions were skewed towards the majority classes. So this is a common issue with imbalanced dataset where some categories like benign lesions appear far more often than the malignant ones. So as a result, the model learned to play it safe. So it basically achieved decent accuracy by predicting the dominant classes, but performed poorly on the minority ones like the melanoma or the vascular lesions, which are actually the most clinically significant. So with the optimized model, the overall accuracy slightly dipped, but this is by design. So we prioritize fairness across classes. So now new model was better at recognizing underrepresented and critical classes like actinic keratosis and melanoma. So these are cases where early and accurate detection can save lives. So this kind of balanced performance is essential in healthcare applications where false negatives can be far more costly than the false positives. So to wrap up, we have demonstrated how deep learning, when properly optimized, can approach dermatologist level accuracy in skin lesion classification. So, our future direction would involve model explainability, mobile deployment, and expanding to other skin conditions. Thank you.